Good morning, everybody. Welcome to the Colloquium. Today we have with us Professor Suhas Diggavi from UCLA. Suhas got his PhD from Stanford and was formerly at EPFL before joining the University of California at Los Angeles. He's received multiple awards for his research work, including the IEEE Information Theory and Communication Society Joint Paper Award, the Moby Hawk Best Paper Award, and the Donald Fink Prize Paper Award. He's also a fellow of the IEEE, a former distinguished lecturer of the Information Theory Society, and on the board of governors, also of the Information Theory Society. At a personal level, I have had the pleasure of knowing and collaborating with Suhas over the last many years, and it's a pleasure to have him here. And he's going to tell us today about some of the exciting work he's been doing on content-centric networks, wireless networks in particular. Without further ado, let's welcome Suhas.
So thank you very much. It's a pleasure to be here. It's a pleasure to be here, and thank you very much for the invitation. As Professor Kannan was saying, I've really had a lot of fun working with him. And I'm also looking forward to collaborations with Professor Reynolds and maybe other people in the department. So what I'll talk about today is work that we have done over the last couple of years on what one can call content-centric wireless networks, and I'll explain what that is. A lot of the work that I will present is part of a PhD thesis of my student, Jad Hashem. So Jad just finished his PhD last year, and many of the results that we talk about would be part of his thesis. Another collaborator was Nikhil Karamchandani, who was my postdoc and is now in IIT Bombay as an assistant professor, and Urs Neeson, who actually, funnily enough, he was in the first course that I ever taught at EPFL. So he was a student of mine as an undergraduate. And we have actually ended up collaborating and working on many problems together. And so we have many papers together. So he used to be at Bell Labs, and now he's at Qualcomm. OK? All right. So what are the trends in networking and media consumption and data? So there's a huge amount of, if you look at, this was from a few years ago, when it's really going up even further. It's an exponential increase in the amount of data that is being consumed by people, especially in the wireless. And basically, traditionally, how networks are organized, and this has been the case since basic telephony and even the basic structure of the internet, was they were connection-centric networks. What are connection-centric networks? You basically connect from one point or a machine to another point or another machine. And what is happening, there's a trend that started to happen in the late 90s, was that people realized that what the intent of the users is not particularly to connect to an end server, but to access content. And so Akamai was probably one of the most famous and among the first companies to realize this. And what they effectively did was create a content distribution network, where one duplicates data in many, many different locations. And that's called mirroring. And that's basically how almost all the things that you now use on when you stream Netflix, or you stream any of these even from CBS or any of these things, or even if you go to New York Times or any content, you usually go to a mirror site. And the mirror site is sort of some site that duplicates content, is closer to you. And that's essentially how a lot of the wired networks content delivery is done. Now, one of the things that happens in wireless networks is that the bottlenecks that one encounters in wireless networks are actually distinct from the wired networks. In particular, one of the bottlenecks is the wireless communication rates, or one loosely can call bandwidth. And that is resource limited. Another is that because it's the last hop and the edge, you may not have as much memory to store all the content. You can't possibly mirror or duplicate. You actually don't even do that in CDNs, but there's enough, the memory constraints are much less there than here. Okay? So the question becomes, how do you actually design content-centric networks in wireless? So to basically think about this, why would one look for caching? So in particular, the idea that you have resource-limited devices in memory, and the fact that in wireless the traffic is growing, means that what would one want to do? You want to store things strategically in the edge network. And the question becomes, how do you store it? So in particular, the content-centric networks in wireless even the current wireless network architectures essentially use connection-centric, which is basically you connect to a certain end device. But if you go to a content-centric, what you'd want to do is you want to look for content, place them strategically and access them and deliver them accordingly. So in a sense, you need to design both the delivery and the placement together. So how do you do this? So let's actually go back and think about how do you actually architect something like this? So there is a proposed architecture for 5G, which already is in some ways part of the late 4G implementations, where you have a base station and what used to be called femtocells, now called small cells, and there are many other names for it, are essentially very local, small range, high data rate links that access points can have. And so the idea is that you endow the base station, which in particular can grab content from the wired network as well, to have essentially the content that one may want. But you also endow the base stations to have some small amount of memory, where you can strategically place part of the content in the access point. So the placement phase is basically to place some part, and we'll have to figure out what to place here at the different access point. And you need to do that, of course, before you know the demand. And so when users come in with demand, you need to assign, based on what you have placed, to which caches or access points that you give it access to. And then, of course, not everything is stored there, so the base station will still need to deliver to resolve the content request. So that is the basic architecture we propose that combines the caching with the proposed 5G architecture of wireless. Okay? So how do we go about doing this? So what is caching? So let's step back and think about what exactly caching means. So you basically have these access points, and you want to place the content there. And then you place it before the request, and then in some ways, the delivery is to deliver the missing stuff that is not available from the local access. So in a sense, the main technical problem we will look at is a trade-off. So the trade-off is the following. If your cache size is so large that you can store everything, you really don't need to send anything. If your cache size is so small that you cannot store anything, you have to almost send everything. So that's the trade-off. The network load, that is the amount of stuff you need to send, versus the amount of memory that is available to store. Okay? And in all the problems that we will talk about, this is the trade-off we will try to examine in a fundamental theoretical way. Okay? And if you had questions, please feel free to interrupt. All right. So let's try to understand this in the context of what one can call conventional or uncoded caching. So let's say you have two files, A and B. That is the content. The whole universe is just two files. and you have storage enough to store one file at the endpoints. Now, I can do many things, and right now I'm actually being even more sophisticated than what current systems do. I'm going to split the files A into A1, A2, and B1, B2, 2 parts, and I will do that for a reason that you'll see soon. Now, in the usual caching, you will store the same content in all the mirrors or all the locations. So in particular, let's say we store A1, B1, and A1, B1. Both of them are the same. In more conventional terms, you would have stored A and A or B and B, but let's make it even more, slightly more sophisticated. Now the users come in with demands. Let's say this guy comes in with demand A, and this guy comes in with demand B. So this guy is missing A2, this guy is missing B2. And the conventional scheme is to send two streams, two informations separately, one sending A2 to this guy, and one sending B2 to this guy. So the total network load that we will have is one file, because it sends this plus this. So it's half a file each, so the total is one file. And the basic question one can ask is, can we do better? And this was basically the main observation is that conventional caching is insufficient for wireless for two reasons. One, which we said about communication bandwidth. But it also doesn't make use of the fact that wireless is inherently a broadcast medium. So when one sends something out, many people get to hear. So when I'm talking now, everybody gets to hear some version of what I'm saying. And another, which we'll come back to at a later point, which we will not talk about immediately, is the fact that when two people talk at the same time, there is interference. And we will try to bring that aspect out later on in the talk as well. So the question becomes, how does one use these properties to do this? So let's revisit the same example. And this was done by Madha Ali and one of my collaborators, Neeson. And this was a very nice paper they published a few years ago, which essentially used the idea of network coding effectively. And the idea was, coming back to the same question, you have A and B, and you're allowed to place anything you want before the demand is known. So what do? You basically you place not the same thing, you place A1, B1 here and A2, B2 here. So you're not placing exactly identical stuff. Now let's say that this guy comes in with a demand A and this guy comes in with a demand B. This guy is missing A2, this guy is missing B1. So now you can satisfy both the demands by sending the XOR of A2 and B1. Because this guy knows B1, he can remove that and figure out A2 as he requires. And this guy basically knows A2, so he can remove that and figure out B1. Okay? So therefore, now I'm able to send something which is through a broadcast link, maximally useful to both of them, and the amount you have sent is half a file, not one file. So you have gained in terms of the amount of network load that you have placed. So the basic idea is that in general, you want to, this is a very simple example with two, but the question becomes, how do you do it in general? And you want to when you have a lot of content, you have to figure out what to put in each of these content. And then the basic idea is that the server then sends something that is useful for at least a subset of them simultaneously. And basically, the amount that you do is depending on the cache memory. So in particular, for example, when there's very little memory, you will have if there's no memory, you have to send individual. There's nothing much you can do, right? There's no local storage. You need to send satisfy the individual requests. The only advantage you can have is if two people ask for the same file, they can use the broadcast. But otherwise, you don't get any advantage. So when you have very small amount of memory, the set of people that you simultaneously satisfy becomes small. And this is sort of illustrated by this picture. If you have sort of medium-sized memory, you may get to simultaneously satisfy more people. So maybe the multicast size is slightly larger. So this is maximally useful for groups of 3 in this particular example. And when you have very large amount of memory, effectively you can send sort of more common broadcast. And this is basically a sort of the trade-off that you can have depending on the amount of memory and the network load. So you see that here, in this case, the network load is the smallest, and the memory is very small, the network load is the largest, and that's the trade-off. And this was characterized by Madha Ali and Neeson for uniform popularity, and they showed a significant gain. So this is a scaling behavior of network load versus cache memory. In conventional caching, you sort of get a linear decrease, whereas here, except for the very small memory regime, you're getting an amount of network load which is approximately independent of the number of users. So which is a significant difference in terms of scaling. Okay, and that's basically the reason why a lot of interest came up in trying to understand this in a more general context. So what we will talk about is thinking about this in many different aspects. One is to think about, so this was done for uniform content popularity. Now, content in media and definitely in the internet is very, very non-uniform. There are very few files that are accessed a lot, and many, many which are almost never accessed. And so does this hold up even when there is very strong non-uniform content popularity? And that's the first thing that we will talk about. And we will also talk about how to allocate and match the different access points to depending on the content request. Then we will focus on an architecture which combines the physical layer and the caching, and we will prove a separation architecture is actually quite good. And then we'll go to not single hop but multi-hop networks, and depending on time, I will sort of modulate the length of each of these discussions. Okay? Any questions about the setup? Is everybody okay? All right. So let's start off with the question about file popularity. So the file popularity, there are many, many different ways of thinking about it. One is, of course, all the files are equally likely. And that's basically the model that was proposed in the original work on coded caching. But we know very, very clearly that the distribution, for example, this is YouTube data. This is a fit for what's called a ZIF distribution, so power law distribution. So if you look at the log of the popularity versus the number of versus the files, you see a sort of inverse polynomial behavior. So that's sort of the ZIF power law. There are many other popularity models. There are, if you look at depending on the different data sets, but the main point being in all these things, it is very, very non-uniform. Some of the content is very highly accessed, some of them really almost never. So the question becomes, how do you do caching in this context? Okay, so we have done these popularity models, ZIF as well. We'll see that later on. But the simplest one, and in fact, in many cases, in fact, we actually ran on data sets, and it turns out that this one is not a bad fit, and it's actually analytically also a nice one, is that you don't actually fit a continuous curve to this. In fact, even for probability estimation, you'll never do that. We cluster them into groups. So there's a set of files which have sort of similar popularity. You put them in one class. And next set of files which have similar popularity, we put them in the next class, and so on. So this is what we call a multi-level popularity model. And that's sort of what we will work on for the next few minutes. Okay? But you can also fit this back to other models as well. Okay? So, yeah?
When you say arbitrary, what is it?
Any distribution. Any distribution. Give me a probability distribution. That's it.
You have the results for the arbitrary.
You can modify these results to do this. I will not present them here, but you can. There are the techniques actually work out reasonably well. But again, it's the most interesting ones are the ones I will talk about. Okay. All right. So you divide the file. This is the multi-level model. That is, you divide it into popularity classes. They have the same popularity within a class, but the class probability is different. That's sort of the multi-level model. Now, we also do two models. And so one of the things that we will look at is going back to the wireless network architecture. How many users are there in accessing a particular access point matters. So for example, if there is a very small number of users versus a very large number of users. And we will actually come back to this situation, and it actually creates a dichotomy. So number of users. So here let's look at the first case where there are many users for a single access point. So for example, if you have a small cell, it might be that there are just 2 users in that cell. It's a very small cell. Or it could be in a small building where there are 50 users accessing the same access point, and it makes a difference. The reason why it makes a difference is that if there are many users accessing the same cache, their requests are going to basically follow the popularity. So you will see so for example, the green files here are more popular and the pink file is less popular. But you will sort of, if you have a fairly large number of users per access point, you'll see that profile in a given access point. Okay, so the assumption for the theory part is that this proportion is the number of users requesting content in each access point follows that popularity. Okay, and this is sort of a reasonable assumption when there are a large number of users per access point. But if you have a very small number of users per access point, in particular, let's just say 1, then there is no such averaging on an access point. So what you will see is that you will see the reflection of popularity across the caches. So in other words, you will see that, oops, I wouldn't want to go so fast. The proportionality is maintained across the caches, not in a single cache. And this actually, these two situations, it turns out, demands different strategies. Okay? All right. So these are just to pictorially demonstrate, this is the two things. Here is the same profile at each cache. And here, for example, this one is like requesting the pink. There's predictability across caches. And then there's, one of the 4 are like that. But you don't know which one. Whereas here, every one follows sort of similar. So this is the dichotomy. Okay? So the question is, are these two fundamentally different? What strategies are good for either? Or there's a single strategy that works for both, and so on. And it turns out that they're very different, and the strategies are different, and there's a reason why this is different. Okay, so let's try to understand why. So I will not go into a lot of the math behind these things. I'll just explain the ideas. And if people are interested, there are papers associated with it where there's much more gory details. Okay. All right, so the multi-user setup, the basic idea is the following. The basic idea is that you have a certain amount of memory, and you have these popularity classes, and you end up sort of sharing the memory across these popularity classes. So in a sense, what you do is that you take a part of the memory, allocate it to a particular class, part of the memory allocated to another class, and then sort of do this allocation, and you'll optimize over that. In the single user setup, it's actually a much more drastic strategy. What you do is that you take a set of popularity classes, merge them, and treat it like one popularity class. And the rest, you don't store at all. So it's a threshold. There's a threshold, and the threshold will depend upon the amount of memory you have and the popularity. And this is the right strategy, and we will see why. So it's both of these we will show is information theoretically or fundamentally the right strategies, and they're different. And we will also see that this will not work in this setup, and this one will not work in this setup. Okay? So that's essentially what I'm saying. These are not exchangeable strategies. So in a sense, there are two things that drive these strategies. One is that when you have many users per cache, you want to give more popular files more memory in the cache, and code sort of don't code across the popularity classes. Whereas when you have very, very few users per cache, you want to sort of maximize simultaneous, maximally useful transmissions. And so you code across the popularity levels. That is, when you merge, you have to essentially code across them. Whereas here, you do it, so there is sort of two directions that you're being pulled at. And the number of users determine which of the directions you get pulled. And so that's basically the bottom line. The single user essentially favors this pulling, and the multi-user favors the other pulling. So more formally, this is the multi-user setup. There's a set of users. Every access point has a multiple set of users, and the popularity levels are reflected by the request profile of each cache. And basically, the question that we ask is, what is the rate? For a given memory, what is the rate to memory trade-off for this situation? And basically, what you do is that you take the memory, you allocate some part of the memory to the green files, some part of the memory to the pink files. Now, the interesting thing that happens in this setup is that it is not true that you start to store the pink files only after you've stored the green files. There is a sort of a diminishing returns in storing the green files. So after a certain point of having stored the green files, you will get much more bang for your buck by storing the less popular files. So it's actually not true that you first store all the popular files and then if you still have memory left, you go to the less popular files. It turns out that you store the green files or the more popular files for a certain amount of memory, and you don't store it completely, and you move on to the less popular ones and so on. So that's actually a sort of non-intuitive thing that happens in this case. Okay, so the optimization problem you can set up is that each of them gets, each level gets a certain fraction of the memory, the fraction being alpha I, and then you do this placement, and then the total rate, that is, you treat the popularity classes separately. You sort of separately send, think of them almost like a uniform distribution within the class. You deliver it. And then the total rate is, of course, the sum of all the classes. And of course, the optimization will be to optimize the alphas. Okay? And that's something that one can actually, we have done. Now, the question becomes, so here's a strategy. So there is a sort of three kinds of classes of files. One is a set of files that you fully store, a set of files that you sort of partially store, and a set of files that you don't store at all. And our optimization will tell us exactly what to do. So this is a scheme. Now, the question that, as an information theorist, or as a person who is also interested in theory, you say, okay, this is fine. This is a scheme. Could I have done better? And in fact, what one can show is that this scheme is approximately optimal. I will not go through an information theoretic argument to show this, but this is something that you can find in our paper. So basically, the idea is that you can show as a scaling behavior the rate that this particular scheme that we can get, and any scheme with no constraints on the kind of placement, no constraints on the delivery mechanisms, how much it can do. If you take the ratio, it's at most a constant. So you're a constant factor away from the optimal. And with just for people who may be interested in the technical things, what makes it new is that actually the lower bounds that we needed to get were actually interesting tools that were what are called non-cut set bounds in the information theory literature. Okay? Yeah.
There is also no intra-popularity coding?
So in this case, what you're doing is that you basically, there is intra-popularity coding in the sense that you treat a class as one unit. So if each popularity class is given a separate memory share and treated separately. So just like you had in the uniform case, if you call that intra-popularity coding, then there is coding within the class. But you're not doing you're not coding across the popularity classes. Yeah.
So Is it that there's, I was thinking, is there a threshold in which you actually go from multi-user to single user? Because there's nothing special about single user.
Yeah, so we will come to the single user in a minute. Okay? So now let's look at the single user setup, which is now you have the profile is across the caches. And we just look at one user per cache. And basically now, we don't answer that question in particular. We believe, and we have schemes, but we cannot prove a converse, so to speak. So we believe that there is a behavior which can meld the two. So this is true for any fixed number of users. And the other one is essentially asymptotically large. When you look at the intermediate regime, there are schemes that we have, but we can't prove a converse to it. Okay. All right, so here, the predictability is across the caches, as we said. Now, many different arrangements are possible, and we don't know which arrangement we are going to be encountering when we do the placement. Okay, so the question becomes, how do you do this? And the idea is really to merge some of the levels and ignore the rest. Treat the merged levels as one uniform popularity unit. And the question becomes which files to merge, which cluster popularity classes to merge, and so on. And then basically the delivery phase is just to send across. For the ones you have not stored at all, you have to send it all completely. For the ones you have stored, you will just use the coded caching mechanism. Okay? All right, so basically this is what I was saying. This one has no memory, so it'll have to be full transmission. And for the ones you have stored, you do the coded transmission. Okay? And the question is which levels to merge. And this is essentially the cutoff. That depends upon the amount of memory and effectively the popularity levels and so on. So you basically merge and sort of store it as one unit, and the rest of them you don't, and that cutoff is essentially what we can determine. Okay? And again, we can show that this is approximately optimal. And in fact, again, the converse in this case was actually simpler than the one which we had for the multi-user case. Okay? So this says that this scheme is approximately optimal for the setup. Then the question becomes, is there one scheme that can work for both? And the answer is no. And if you look at the memory sharing scheme, it is sort of not using the fact that you can have coding opportunities across the popularities. Because when you have a single user, you only have profiles across the caches. Okay? And in fact, you can show that it's not order optimal. And if you use the other strategy for the multi-user setup, it doesn't efficiently use the memory, because some of them you want to give more memory than others. You're not using that at all. And again, you can show that this is not order optimal. And so basically, so there is here's a quick summary. So when you have multi-user, you want to do memory sharing, it doesn't quite work for a single user. And threshold and cluster doesn't quite work for the multi-user, but works for the single user. So that gives you a dichotomy, and actually says that depending on this behavior, you will actually may need different strategies. Okay? Now, one thing that we did here was the fact that a user was pre-assigned a cache. It may have not been clear to you, but essentially in the access, what you are always attached to a particular access point. So for example, in current wireless systems, the way you get attached to an access point is highest SNR, or something like that. Or could have load dependencies, but that's sort of so there is a particular access point that you're assigned to. Now the question we can ask is, what if that changes? So let's say go back to the architecture. So there is a base station, and then there is access points which has the thing, and then of course we have done placement before we know the demand. And now the users now request things that they want. Now what you can do is, instead of fixing this user to this particular access point, maybe this access point had a better SNR for this purple user, but he could potentially get, if he can see another access point, he might get attached to that access point instead. How will this change the situation? This is what we call adaptive matching. So the question becomes, who connects to what, and so on. So let's look at this idea. So the main idea is that in fact, even now, when I sit here, I can view or see many, many access points. I may have a choice of connecting to any one of them, right? Instead of getting pre-assigned. So my connection could depend on what I'm asking for. And this is actually something that is done a lot in the wired networking literature, but was not really done in the wireless setup. So the idea is sort of a matching phase. The matching phase being, once I have asked, the placement is fixed. You do the placement again before you know the demand. The matching phase says that once I come up with a particular demand, I can be asked to access some particular access point. Now, of course, what you want to make sure also here is that there's a load constraint. In other words, not everybody can access the same access point, because now if you can match, it may turn out that everybody wants to attach to the same access point. You don't want to do that. So there is essentially, in this theory setup, we have one cache per user, or one user per cache, but you can have just any load constraint placed on it. Then so the number of users that can attach to a particular cache may be limited. So the question becomes, how do you now match them, and then how does it perform? So the interesting thing is, how do you actually compare it with the other scheme that we had, the coded caching scheme? So in the coded caching scheme, you basically can attach to a particular access point. In this case, actually, if you have given a particular access point to work with, it may not necessarily be efficient. So let's go back to this situation. So here is a model that was studied a few years ago, which is what we can call global. So in a sense, this is sort of extreme in the sense that I can attach to any cache in the whole universe, and I want to match it. Okay, so if I'm able to attach to any cache, you do a placement where, of course, what you effectively do is that you make copies. The placement phase is very, very simpler than in the coded caching case, where you replicate content. And that's exactly what the mirroring schemes of current content distribution networks do. They don't split up things and so on. They just place content and duplicate content in different locations, right? And then what you do is, when you ask for something, you go and get connected to the place where the content exists. Right? That's really what the CDNs do. Now, what happens in the wireless setup? So in a sense, and so of course, if the content you're asking is already in a place where you cannot connect to here, because the load constraint is violated, then of course you have to get it directly from the server. That's the main idea. So what we showed, what one can look at is sort of a memory and rate trade-off, and looking at the amount of memory. And so it turns out that beyond a certain amount of memory, the coded caching is actually inefficient. So if you're allowed to do matching, it turns out that you don't need any coding. You actually don't need any coding. So we actually work with beyond a certain memory, where you are essentially being able to duplicate content in the right way. You don't need any coding at all. It's a much simpler strategy. So the matching will take care of everything. So in fact, that is sort of also explaining why, when you have sort of very large amount of possible places you can connect to, you don't necessarily need coding. Okay? So the question we asked is sort of, there is a dichotomy. When users are matched to a fixed cache, the coding is useful. When it can be matched to any cache, replication is good, and you can essentially, coding is not that efficient. The question we asked is, this one is very optimistic in the sense I can connect to any cache in the world. What if there are only a subset of caches I can connect? There's a cluster. So that sort of says that, for example, I'm in this building, and I can only see 10 access points. I can't see all the access points in the whole of Seattle, for example, right? So I can only access 10. Now, how large should this number of access points be where coding is useful or not useful? Or is there a better scheme even than this? And so here what we show is that the model is that you have clusters and users can only request in this cluster, and there's a load constraint, of course, again, as before. And the matching phase is that you're allowed to match to your particular cluster that you can access to, okay? And of course, this is the usual delivery phase. And again, we ask the same question about trade-off between memory and rate. And we now use the fact that you have ZIF popularity profiles. It's easier to deal with in many ways, but all the mathematics here can also work for multi-level. We believe it will work for multi-level popularity as well. So here D, the cluster size is D, so that's something to remember. So the cluster size that we're talking about is D, okay? And beta is the slope of the ZIF. So larger the beta, the more skewed, the more non-uniform the distribution is. The beta equals 0 is uniform and it goes up, okay? So this is sort of uniform, store uniformity in the cluster. So now we are talking about adaptive matching. So when you are more and more skewed, you'd replicate content more, and here the less popular ones you make fewer copies. Okay, so in the uniform case, you don't do much. You basically everything is the same. When it becomes larger than beta, so up to beta equals 1 roughly looks almost like uniform. When you go over beta equals 1, that's when the non-uniformity kicks in. So there, you replicate here these files a lot. This one, you only put 1 copy, and the rest you don't put any. And if you keep going up, oops, I don't know why it keeps slipping, okay. And so that's basically how it works, okay? Now, in the static matching, this is something that we had already seen before. We had done in the earlier case, right? We did it for the multi-level, but it also, as I said, it works for the ZIF. So here, what we saw was that when beta becomes large, you basically do a threshold and merge. So here, these ones, you sort of all merge into one level, store them all, treat them like one popularity class, and the rest you don't do anything. And that threshold changes as the slope changes, okay? And what we can show is that for the uniform case, essentially this threshold where adaptive matching, it depends on the cluster size now. The larger the cluster size, the more dominant is the adaptive matching because you're getting a larger and larger universe that you get to see. The smaller the cluster size, the coded caching becomes more and more efficient. And there is a threshold, depending on the memory and the cluster size, which tells you which one will dominate, okay? And that threshold, as I said, changes as this happens, okay? And you can actually create a hybrid scheme which combines both of them, and I will not go into the details of this, but yeah, I'm happy to talk offline, or you can look at our paper, which combines both of them, which dominates both, which combines the coding and the adaptive matching, okay? And in certain regimes, we can actually show that that scheme is information theoretically optimal as well, okay? Now, basically what this says is that in some sense, depending on the cluster size and the popularity, one can actually, may not necessarily, you may not need to do coding at all. You may actually do replication. And so you have to design your system carefully. And this gives you a design principle of where you do this. Okay. Now, the next thing I want to talk about briefly is till now we've been talking about caching as if the delivery is like bit pipes. And we know that wireless are not bit pipes. There is a wireless, it's a noisy channel. There's a physical layer associated with that noisy channel. The question becomes, how do we actually, is there a connection between how you do the physical channel with the caching, which is now assuming effectively till now error-free bit pipes? So how do you deal, so basically here is where we bring in both the broadcast and the interference. So in a sense, you have multiple base stations, and this guy is trying to send some stuff, and he can interfere with other people. So this is an interference channel. And the question becomes, how do you actually do you need to come up with a very complicated scheme that combines the physical layer and the caching? Or can I come up with a separation architecture and say something about it? Okay? So here is the idea. You have caches, which basically have the content. Now you can essentially think of this as almost distributed transmission, because these guys have part of the content, these guys have part of the content, and there's a set of users who need this. Now, these two guys cannot coordinate among themselves because they're two different base stations, but essentially can sort of deliver stuff. Okay? So the idea is that now there is physical layer interference. So as I was saying, if I talk and there's somebody else talking, the signal that the receiver gets is a superposition of the two. So the question becomes, now the way you think about it is that I want to send the information in the fastest possible way. That is the actual transmission rate that you want to send. And the trade-off is, of course, again, with the amount of memory. Now, the memory could exist both at the transmitters as well as the receivers, the caches in both locations. So one way is to say, OK, let's try to just do sort of multiple broadcasts. So in other words, you take this, and then this content memory, and then each transmitter stores part of the content. And then you place some, at the receivers, you place some content. And then what you do is that once the demands come in, you basically this guy sends some broadcast to the different users. And this guy sends some broadcast, like before. Okay? Now the question is this a good idea? And it is sort of in the right track, but actually turns out is not a good idea. And the basic idea is that you're sort of, this guy is completely silent. You're essentially not using the fact that this can also send something. And basically, very few users get stuff at the same time. So that's the inefficiency in this. And we can be much more efficient, especially for smaller memories. And you can actually even for larger memories. So let's say that you have no receive memory at all for a moment. So each receiver gets a part of the requested files. So this is sort of if two people come in, this guy sends something, this guy sends something. It's a superposition of them. And essentially, you could, in principle, use methods, physical layer methods, which are called interference alignment and so on, to make this more efficient. Okay? Now, the question becomes, is this the right thing? Here, what you're effectively doing is that you are sending sort of broadcast transmissions here, and you're creating maybe message-level private links to them. So in a sense, what you're doing in an interference channel is that as a bit pipe, you're creating private messages from one transmitter to one receiver. Okay? That's really what the bit pipe version of the interference channel is. So this is not very useful when basically perhaps you're not using the fact that you can address a multicast group. And the basic question we ask is, what to send and how to send it is what you need to ask. So what to send is sort of, in the first strategy, we said, OK, one message from each transmitter to receiver. That's really what we are sending. And the way we are sending it is by simple time sharing. Can we do better? So we can send one message from each transmitter to each receiver, and you can send it using interference alignment. That's sort of another mechanism. So both these mechanisms are what are called, we can say, almost separation. In other words, physical layer is creating a certain topology of message bit pipes. And you're riding on top of it to do the caching. Now the question is, what is the right interface? So the two things that we looked at was one transmitter to all receiver. It's like a broadcast. Another one was one transmitter to one receiver, which is sort of unicast in some sense. But you actually can do something more interesting, which is you can take subsets of the receivers and create multiple multicasts. And that's basically the question. What is the subset size? And in fact, how do you choose that depending upon the amount of memory? So to redraw the setup, this is what we create. This is what we call a multiple multicast, and if somebody's familiar with it, it's X channel. Okay? So where each node has a message for a subset of the receivers. So that's the multicast set. Size of the subset depends upon the amount of memory you have. The smaller the memory, the size is smaller. We almost go down to unicast. The very large memory, you have the whole universe. You broadcast everywhere. And the memory dictates the subset size. And you basically do the physical layer is, the only thing the physical layer is responsible for is creating these multicast sets reliably. And then the network layer rides on it. Given this multicast set, it does the coding. Okay? And essentially that's sort of what ends up happening. So you split the library, store each sub-library, use this multicast set, and send that. Of course, this is a scheme. And what one can show is that this is approximately optimal. So in other words, this separation architecture is indeed the right interface between the physical and the coded caching layer is the right message size, subset multicast set size that you want to use. Okay, and that's basically optimal. So the last one, with a few minutes that I'll talk about, is multi-hop networks. So if you have multi-hop networks, suppose here, think of it as a base station and then access points, and access points themselves are broadcast networks. Okay? So the question becomes, how do you store in multiple layers of this? Okay? So we want to characterize the rate region R1, R2, for a given memory size. So there are 4 parameters here. And is coding across multiple layers useful? And is there a trade-off between these rates? So there are 2 very simple strategies. One strategy is sort of, think of it like each layer behaving like a receiver. So suppose file A is requested by a subtree here. This node basically decodes A and B, which is meant for something below. So you do sort of the caching for this layer separately. And then this one becomes the transmitter and does the thing. This is one strategy. Okay? The second strategy is a forwarding strategy, in the sense that the middle layer does nothing. It just sort of forwards whatever it gets to the relevant things without essentially decoding. Okay? So if this has a request for A, this guy sends something useful for A, and this guy just forwards it. It never gets to decode it. These are 2 possible strategies. And what we show, the scheme is essentially a combination of the 2. It's actually a memory sharing and time sharing version of these 2 strategies. And what we have shown is essentially the fact that this combination is actually information theoretically optimal within a constant. And it's actually, we've characterized these regions, so it's within the region itself is a constant away. And so this is sort of the inner and outer bounds. So this is the fact that the optimal regions can be sandwiched between a constant factor away from the achievable and what we showed is that you actually don't need to code across these multiple layers. And in fact, sort of almost asymptotically, it looks almost like there's no trade-off between these 2. Again, this is very short. If you want to look at it, this was a paper we had in the Transactions Information Theory a couple of years ago. All right, so let me stop here by giving you a quick summary. So what have we argued for here? What we have argued for here is that in wireless, the content-centric networks, when you have to do strategic storage and delivery, you have to be careful in how you do this. The placement has to be done carefully, and the delivery, of course, as well, has to be matched to it. And there are many interesting situations. One, when we have very different popularities, it depends upon how many users there are in the access points. Very small number of users to very large number of users. Strategies are different. And when you allow for matching, Again, it depends on the cluster size, how many you can match to, and so on. So this says that when you design a content-centric network for wireless, you now can sort of use the right strategies depending on what the theory is said. Okay. One of the things that I think is a larger architectural question, which is I think what this suggests, is that a lot of times one of the successes of the internet is the layering architecture, where one does not couple the physical layer with routing issues and other things. This is suggesting a similar layering architecture for caching, where what one does is that there is an interface, the right interface between the physical layer and the caching is the kind of message sets that you are creating, the right multicast set. The caching says that this is the multicast set that I want. The physical layer then becomes responsible for delivering that reliable bit pipe of that multicast set. And I think this is a principle that will hold for many, many other situations. This is a particular example for interference networks, but I believe that this will work for almost every other network that we can think of. So there is a nice separation architecture that one can think about. And finally, we can also extend this to multi-hop networks and so on. And I think this is sort of where we are, and there are many other interesting open questions, and I'll be happy to take questions.
Any questions?
Yeah.
Thanks, Suhas, for a wonderful talk. You mentioned about Akamai, and we know that Tom later is the 2018 Marconi Fellow on CDN. So I was just thinking, is there any CCN in the market now?
So CCN. So I have to say that. So the question that was asked was, are there CCNs in the market? So now, actually, there's a very interesting whole, in the last 10 years, there is a whole networking community has gotten into what is called CCNs, and or also called ICNs. So there, the goal is not about what we are talking about, but more about sort of overlaying the routing based on content rather than on. So currently, almost all routing schemes are based on connecting the best route, or depending on load, from point A to point B. Yeah, so here the point that they're doing in content-centric networks is to give a routing based on content rather than on endpoints. So there's a whole field in networking called CCNs, essentially, or ICNs, doing this. So what distinguishes what we are saying here is that we are looking at the wireless edge rather than looking at the wired internet. So there is a huge amount of literature and work which is done in trying to figure out where to place content and how to access the content. So one can say, okay, I will create a routing table and then do that. Is there a more direct way? So there is a whole effort called Internet 2.0, which tries to do that.
So it sounds like the standard 802.11 networks wouldn't support this kind of traffic. Is that right?
The current networks, yes, because they don't allow for some of the things that, but you could modify them, yeah. No, he was asking not about that. He was talking more about the wired network, because Akamai is a content distribution network more for the wired network, where you mirror sites and so on. But there's a more nuanced version of it which is being developed, which is the different ways called content-centric networks, etc., where you essentially Akamai itself is an overlay network. and the other ones are also overlay networks at this point. The proposal is actually to also change the internet architecture to not just make it an overlay, but all the current implementations are overlay.
Yeah. I've kind of a related question. So, kind of following up on what Faith was bringing up, in the WAN case, the 5G case, right, you have homogeneity among the base station architecture because they're owned by one entity and managed by one entity. But then you look at the LAN case in our buildings or whatever, they're very heterogeneous. So is there any hope for a single strategy that would work in both cases, or is it kind of doomed to be different?
I think the problem is that all the delivery and placements have to be within a domain, because there needs to be coordination in that. What one could potentially do is an overlay through bonding, right? That is one possibility. So in other words, in bonding, what you do is that you get partial content from one service provider and bond it with partial content with another service provider. That potentially might be feasible.
I have a quick question. How much channel state, about popularity, about the files and global information is needed to make these schemes work?
I see. So the popularity in the time scale that we are looking at is assumed to be known. However, there has been work on what you can learn online. So in online, what do current strategies do? So for example, they do least frequently used and other things, right? So essentially that's sort of like adaptively learning the popularity. And one can, we haven't done it, but I think people have done sort of not in this context, but other contexts they've tried to look at online versions of this where you learn the popularity as you go along. About channel state, at this point, the results that we have for the inference channel, of course, it does require it. But I don't believe that's a very delicate assumption. I think we can prove architectural results without that. Yeah.
Have you done any work trying to distribute content amongst real devices using these schemes?
So we had tried, one of our students, we don't have any papers on it, but we had a couple of summer students and my PhD student actually implemented this for video streaming. But we never really published it or completed that. Yeah. There are many interesting challenges that come in going from the theory to the practice. One of the biggest challenges is sort of, which is hidden in this talk, is sort of the number of, remember in that example I gave you where I split the file into parts? When the number of users and caches grow, that splitting becomes larger and larger. That's actually an important practical thing. You don't want that to become too large. And the theory does not quite match that. So there's an interesting theory question as well in terms of how do you, if you have a limited amount of sub-packetization, so to speak, how do you do this? And that actually comes up in the practical implementations because there you will limit it. Okay.
If there are no further questions, let's thank the speaker for the excellent talk.